prime. So the first virial coefficient, okay, so let me just write down over here that this is my virial expansion. So the first virial coefficient is the most important one. And these coefficients, these are dependent on the temperature. Right? We'll not go into so much details right away, but believe me, these are dependent on the temperature. And for example, B, let's plot this as a function of temperature. B. Then at a certain temperature, the B just crosses over like this. Okay, so it just changes from negative to positive. Yeah. Which means your interactions are turning from repulsive to attractive. Okay, and this particular temperature is called the Boyle's temperature. And so if B is equal to 0, essentially dZ by dt is equal to 0, or Z approaches 1. So this is when the intermolecular attractions and repulsions cancel each other, that it seems as if it's behaving like an ideal gas, but it's not. It's not behaving like an ideal gas. Okay, we'll not discuss these things in more details, but they're definitely there in the book. And yeah, I'm going to follow most of Atkins, so you could just look at that. Most of the things are there in Atkins. Okay, so now think about, we've been talking about these interactions, and the two assumptions for the ideal gas that we saw was that these molecules do not interact and that they do not have a volume. So let's say if they actually have volume, so if they have volume, then I would say that my ideal gas equation could be changed like this: V minus some, so V bar, yeah, is equal to RT. So, and let's say that this B is some kind of a volume of the total number of molecules. Okay, no need for this here, right? Okay, and what about the pressure? Yeah, the pressure stays like that. No. So now this P into V molar minus B, right? Okay, so this is not volume, but let's call it molar volume, some kind of. Okay, it's not exactly the molar, it's something more than that, but let's call it some kind of a molar measure of the molar volume of the total number of molecules. No, then it doesn't say total number of molecules. Measure of the molar volume, right? Now you think of let's think of this box where we have some molecule, okay, and this particular molecule is going and delivering, it's going and hitting the wall, right? And when it hits the wall, you get a pressure P. Now this pressure P was assuming now for the ideal gas that this does not interact with any other molecule. But if we have some more molecules in the vicinity, so they would be rather pulling these molecule towards itself, and the pressure exerted would be slightly less, right? slightly less than what it actually was if it was an ideal gas equation. So to account for that, yeah, let me add a term to the actual pressure. So the pressure exerted is like P, that is what I have measured. But if it were an ideal gas, it would have exerted some extra amount of pressure, right, plus A. And to make dimensional consistency and also normalized by the molar volume, let's just put this, don't worry about this, but this is the pressure that is exerted if the gas was ideal, right? And that's it. I'll just get this equation back. Okay, so that's your van der Waals equation, and that describes a lot more than your ideal gas equations. It describes the real gases a lot more. We'll talk about this in the next lecture.